Okay, so now I will continue with the last part, how we can do spatial temporal recommendation. So let's first look at the background. So because for most of the existing recommendation, usually we consider we are doing like some online recommendation, right? Recommend movies, products, which can be just registered to some online systems. But in real life, okay, there are a lot of situations we will see that spatial and temporal information play a very important role. Okay, so even like for some social network like Foursquare, Facebook Places, Instagram, right? So people actually can do some activity like check-in. So now this kind of check-in activity actually can connect you from the online world to the offline world. Right. So for me, actually, I do not quite use this kind of location-based social network, but I believe many of you actually do use them. So essentially, when you go to some places, for example, go to a coffee shop and grab some coffee, right? So you can use your mobile phone to tell people where you are and what you are doing. Okay, and then other people know, okay, what's your current location and things like that. So essentially, if you look at the information we can collect by looking at this location-based social network, we know the user, okay, and time and location. And in many cases, you know some sort of content information because the user can write down some like comments, a review, and things like that. Okay. So essentially, it can be recorded as like for item record. So we actually can look at the whole thing by this information network, which is called geosocial networks, right? So if you look at the top layer, it's kind of content layer. There are many different things like videos, posts, images, things like that. And the second layer actually is a social layer because you still kind of have your friends in those kind of location-based social network. And in the bottom layer, actually, we have this geolocation information, right? And also remember that we have time. So everything will evolve along with the time. Okay. So what is spatial item recommendation? So essentially, as I said, in most of the existing recommendation, people just consider the online items, okay? But in spatial item recommendation, there are actually two types of items that you can do recommendation and involve with location information. The first is like point of interest. So things like restaurants, hotels, shops, stations, right? So those items, essentially they carry some like spatial information. And the second type of spatial items actually is the events or activities, right? Such as parties, concerts. So actually different from the first type of items, which just associate with like spatial information. The second type actually also contains some time information, right? So how we can do this recommendation? What are the main challenges, right? So essentially, we really need to combine the offline world kind of activity with the online world activity, okay? And so what are the typical recommendation scenarios? So essentially, there are two types of typical recommendation scenario. One is like hometown recommendation. So-called hometown is like, suppose your hometown is like New York, right? So you want to know what you can do like in your hometown in New York, okay? So this is actually not so difficult job because you have already provided enough historic information in that place, right? The more challenging recommendation is out of town recommendation, like me, okay? I actually right now live in Los Angeles, and this is first time for me to travel to Halifax, okay? So I really don't know what I should do here, okay? So because there's no like historic information for the recommendation system, it's also a very difficult job for the system to do some recommendation, right? So now let's see what are the more concrete challenges. I have already mentioned some, like in a very intuitive way. Now let's look at the more concrete challenge. So the first challenge is data sparsity. I briefly mentioned that, right? So there are millions of spatial items in the world, but how many spatial items you can check in, okay? Probably in your hometown, there are a lot of those spatial items, but when you travel to a new place, there could be just none, okay? So like, of course, for most of a recommendation system, you will encounter the data sparsity issue, but for this out-of-town recommendation, this issue is kind of, it's very difficult to handle, okay? And also, a second challenge is like travel locality, right? So most of people just like stay around, like close to your home, right? So you actually do not really do a lot of non-home activities, right? So this brings the challenge like this. So if you just want to look at this user item kind of matrix, which we have seen so many times, and if you wanted to learn the most important latent representation for users and items. Okay, essentially, when we say we wanted to learn some latent representation or do matrix acquisition, we somehow want to do clustering. Okay, so here, if you look at a clustering result, what would be the most straightforward clustering result in this case? Just by the two cities, right? So one is Los Angeles, one is New York City. Okay, so, but actually you cannot get too much information from this one. Not to mention that when you travel from Los Angeles to New York, and what should you do? Okay, so essentially, if you look at the users in that cluster and the items in that cluster, they share no similarity. Okay, so that's how we can do the recommendation. So essentially, we really wanted to design something to bring the gap here. Okay, so essentially, naturally, we form two clusters, which are based on the two cities. Suppose, like some user you free that usually do some activity in New York City and want to visit Los Angeles. Like we want to recommend a very interesting activity or spatial item for him or her. What should we do? Okay. So if we directly apply the club filtering based methods like I mentioned, then people find that if you're going to some place like within 100 kilometers to your kind of hometown, actually the traditional club filtering method can do a great job. But if you travel further than that, okay, so that is kind of typical activity radius of a person, further than 100 kilometers, then typical, so if you look at the performance, it's kind of just doing random guess. Okay, you cannot never do a good job for this. It's very natural because for us, for example, for me, okay, I'm living in Los Angeles, and sometimes, occasionally, I'm willing to spend like 1 or 2 hours and travel to a nice restaurant, but more than that, okay, I will never do it. Okay, so that's kind of very, very reasonable. And also, we will see that actually people do have different behaviors when you in your hometown and when you travel to a new place, right? For example, in my hometown, not my hometown, but my home base, I usually am interested in public restaurants, right, and public museums, right? But if I travel to a new place, like Las Vegas, right, what should I do? Okay, probably I'm not going to just try to sample all different kinds of restaurants. Probably I'm going to try casino, which I have never done before, right? But this is kind of a typical thing you want to do in Las Vegas, right? So people's interests really will shift when you go to different places. So this is also something we need to take care of. Okay, so all the previous things are about like spatial kind of challenges, and time-wise, they're also kind of challenges. It's like for people, actually, what you have done before also is very important to determine what will you do next, right? So for example, you have already have some like good activities in restaurants or things like that, then probably you will consider to have a movie after that, right? You want to watch a movie after that or go to some bar after that. So it's very natural to observe such kind of sequence in real life. And we really need to utilize this kind of sequential inference for us to take advantage of the temporal information to do the recommendation. And another thing that we will see that there are a lot of like patterns in the temporal behavior for people. Like people usually do something at some certain time. Okay, for example, at noon, people usually go to lunch, and around between 6 to 8, probably people want to go for dinner, right? And this pattern does not happen like daily. Okay, in many cases, this pattern is like has some weekly or even yearly kind of effect. How we can capture this kind of seasonal effect is also a big challenge. Okay. So to summarize all the challenges, we will say that spatial temporal recommendation is rather different from the traditional recommendation. So of course, like in terms of spatial factor, data sparsity is much more severe than the traditional recommendation, although data sparsity is already kind of a big challenge for the traditional recommendation. And people usually just spend most of their time in their like home base and travel very occasionally. And also people do have different kind of interests when they travel to a new city compared to their home base, right? And temporal-wise, we can say that what you have done previously actually have a huge impact on what we will do next. Okay, and also like there are different cycles. If you look at our temporal pattern, how we can automatically capture those patterns, it becomes a huge challenge. So that's why we try to propose methods to like address the spatial factor and the temporal factor. Actually, there's also a method that combine the things together, but I find that Hongzhi, who is the kind of author of all this work, who are not able to attend the conference because of visa issue. I don't know why he didn't put that work. I really like that work, but anyway. So I will try my best to explain the models he provided, and then briefly mention the work that combine them together. Okay. So now let's first come to see how we can address the data sparsity and travel locality kind of a challenge in the spatial recommendation. Okay, so this is a picture we have seen before. So it's like there's a gap between the two cities. Okay, so if we directly do the cluster filtering, actually naturally it forms the clusters in terms of the cities. So now suppose like if a user like usually based in New York and he or she will travel to Los Angeles, how we can do the recommendation and what will be served as the bridge to connect the two parts together. Okay, so essentially we cannot directly look at items because for a spatial item, either it will appear in New York or it will appear in Los Angeles. It can never appear in both places, right? But still they share some common things. Okay, so if you look at the content or topic those items, spatial items belong to, so even they carry different names, right? But still some of them are restaurants, some of them are kind of shopping mall, okay? Some of them are like a movie theater, right? So although they share, they have different name, but they share a lot of commonality. So the general idea is that we'd like to use this content information as site information. Okay, so remember like in the first part of the talk, we say that actually those items can be linked to many other things. So here we can also utilize those additional stuff here, probably content information, to bridge them together. Okay, so that's the smart part. Okay, so that's one thing we can do. And in order to solve the challenge that when people go to different city, actually they probably will have different behavior, right? So they go to different types of places. So this is called like interest drift. So in order to capture this kind of drift, we decided to also leverage the wisdom of the crowds. So we wanted to tell people, okay, for most of the people in the city, what will they do? Okay, so it's kind of it's different from the personal interests. It's kind of the location interests. So it's like everybody come to this place, most likely they will do something. Okay, so it's kind of location-based interests. So the intuitive idea now is like how we can infer what people will do in a new place. Like first, we're going to capture the personal interests, okay, for some person according to the behavior we have observed. And second, we're going to capture the cross preference in that region, and we combine them together. Okay, so essentially, what would be the recommendation query right now? Okay, so previously when we do recommendation, like we're going to recommend something for a user. So the user will be considered as a query. But now the query is like a user and a location pair. It will be considered as a query as a whole. Okay, a pair of user and a location. Because we're going to recommend different things for the same user, even for the same user when he or she appear in different places. Okay, so now let's see how we can implement this intuitive idea. So how we can model this personal interest and how we can model the crowd's interests for a particular location, right? So essentially, we use an idea very similar to the topic modeling. Okay, so we're going to use the kind of topic distribution to describe the personal interests and also the crowd's interests. Okay, so for topic modeling, probably this is just a very brief introduction. So this is like suppose we're looking at DBLP, this kind of a data, and then for different research area, actually we can use different term distribution to describe this different topic. So in the spatial item recommendation setting, similarly, we can also find different topics. Like topic 1 probably is like a restaurant. Then you will see, okay, what will be the restaurant list in that topic and things like that. Okay. So now we propose this LCA model. So you can just imagine it's kind of probabilistic model. So due to the time and also due to the familiarity of this work, I'm not going to the detail, but I try to kind of deliver the main idea how we can construct the model. Okay. So essentially, very similar to the topic modeling, right? So for the topic modeling, actually we wanted to automatically identify the topics. Okay, and each topic is described by a word distribution, and for each document, actually it's associated with some theta. This theta tells people like what percentage that this document belongs to each certain topic, right? So similarly here, we wanted to automatically identify the topic in this spatial recommendation setting, right? So that could be like restaurants, shopping malls, and things like that. And for user interests, suppose like 10 different categories in terms of spatial items, then for each user, we can also use a theta U to denote what's the general interest of this user. Like 20% belong to maybe restaurants, maybe 10% belong to shopping mall, and the other like percentage belong to other categories, right? And similarly, for the crowd preference of the city, we can also have a theta L. So remember, for the crowd preference, actually is a kind of interest distribution for this particular location. So we use subscript L to denote this crowd preference. Okay. And also, we're going to design this switch variable. So in other words, we need to know that at a certain circumstance, how much we should trust a user's personal or natural interest, and how much we should trust the crowd's preference. So you can also have this intuition, like different people may be influenced by the crowd by different percentage, right? So some people, like, they really wanted to do whatever the crowd's doing. So then you will say that when we combine the two things together, you need to put a higher weight on the crowd's preference. But some people, it's like he or she's just a foodie, okay, at whatever place, he just want to find the best restaurants. So in this way, you need to assign much higher weight to his or her natural or personal interests, okay? But all these things should be automatically learned from the data. I will skip the graphical modeling part, but I will use this picture to illustrate the main idea, okay? So the first layer, okay, so essentially, this is the user, right? It has some like personal self-interest. This is the location, and also it has kind of location-based interest. And then we are going to use this lambda u, which is I just described, like how much this person will insist his or her own personal interests. And then combined together, then we will have a new theta, new kind of theta, right? So it's kind of mixed interest. Okay, according to the new theta, actually, you somehow can know that, okay, what would be, so actually, this formula. So actually, you will know that, okay, what would be the top items? Okay, so now let's see what exactly it's doing. Okay, so I think by using this example, it will help you to understand. So essentially, by using this weighted linear combination of personal interest and crowd interest, we can get a mixed interest, right? And given this mixed interest, okay, so remember when we do the spatial item recommendation, we should use all the items in that particular location, okay? So then we're going to use all the items in that location and try to compute what would be the top items in that location that also fit, because for each spatial item in the location, you also know kind of the theta. So you wanted to compute a similarity between the two, okay? So the first thing that you have the mixed interest. The mixed interest, one part is come from the personal interest and one part is from the cross interest. And for the spatial item in that particular location, you also have a pre-computed kind of theta. You just try to see how similar these two are. And then based on that, you will know that, okay, what would be the right spatial item in this particular city that I can recommend it to you. Okay. So here, if you look at the trick here that although if you look at item level, okay, at different locations, actually they do not share exact items because for each single item, they can officially appear in one place. They can never appear in multiple places. But the tricky thing that if you look at the content or other like text information, okay, actually they share a lot of things. Right? For any location, you have to have like restaurants, like a movie theater and shopping malls, right? So as long as you can group them into like high-level topics, then okay, actually, for different locations, you will share like similar topics. Then you can kind of bridge the gaps and do a recommendation. Okay. So this is the initial model. So after that, we have done some further enhancement, but I think idea-wise, it will be very similar to this first work. So the enhancement is that I believe the biggest enhancement from the current work from the first work is that right now we needed to compute the recommendation model we need to compute theta for every location. Okay, so suppose at some point you want to change let me find that. Yeah, you wanted to change the granularity of the location. So previously, probably you're based on city, and later you'll find that, okay, city level recommendation is too coarse. Let me go to kind of zip code based recommendation. Okay, then actually you do not that in your model. You have to retrain everything, which is very painful. Okay, but in practice, it's very natural. Suppose like when you go to some new place and you get out your cell phone, and then you see, oh, what I want to do in area, but it's just the place is just too big, the city is too huge. Then I want to zoom in to go to some smaller place, right? So if your recommendation model have to compute the spatial item recommendation at all kind of granularity, actually you can never do that. But if you want to do it online, essentially you do not have that much of time, right? So the solution here is that, okay, let's build a model that it can automatically take care of the different granularity. So the basic idea is that we want to build this like spatial pyramid, okay? So we just have like in the first bottom level, we have the small grid, okay? And then we can build a kind of hierarchical structure and to make this grid coarser and coarser until like everything becomes one node, okay? And previously when we built this like cross preference for a location, we just say, okay, for the given set of location, we want to learn that. But here, what do we do is that we're going to learn that interest for every possible grid here, okay? So for a final level grid, of course, we just use the information here. But for a like higher level grid, we're going to use all the grid in the path. Okay, for example, for this one, if it also contains all the things, we're going to use all the information in the contained grids. So in this way, it's like actually we can pre-compute the kind of theta L for all the like grids at all the granularity here. Okay, so also yeah. So if you don't want to compute here, if you just compute like in the bottom level, actually also in the online version, you can do very simple additive model to just aggregate the theta together to get a like high level interest here. Okay, so you can, here you have different choice depending on the computational power. Okay, so this is my personal understanding. I feel that compared to the previous model, although the probabilistic model is different, but this probably is the biggest contribution. Okay. Yeah, so this is a typical application. So you can actually zoom in and zoom out, and the recommendation will still come in a very fast way. So you don't need to waste the time to wait for the new results. Okay. And for the experiment results, so essentially, if you look at the result, so now we have interested two models, right? So the two models actually performs much better than the previous location-based recommendation. Actually, before this two work, the existing location-based recommendation is kind of very naive. Okay, it's just like heuristic-based or very simple model-based. After we have designed like the spatial pyramid architecture and also consider some other factors like change the previous probabilistic model into this additive model and consider the roles of each user. Like it's like when you come to a new location, you still need to consider whether you are a local people or whether you're a tourist, because for local people and a tourist, you also have different behaviors. By considering all those factors, it turns out the second model performs much better than the first one. Okay. And also, there are some study because we have considered different factors, right? So also, this kind of study can tell you which factor is most important. It turns out that cross-preference is more important than the user's role. So it's like whether this user is a local person or tourist. And also like a spatial pyramid, this kind of factor ranks the third. Okay, but all of them are kind of important. If you remove any of those factors, and the performance is going to drop in significantly. Okay, so essentially for the spatial based recommendation, we have like 3 challenges, and then we propose 2 models to solve those 2 challenges. So now the next challenge is like if we are dealing with the temporal factor in the recommendation, what should we do? Okay, so for this part, it's kind of completely out of my control. So this is all of Hongzhi's work. So still, I try to deliver the high-level message, and then probably we just go to the big summary part. Okay. So for sequential event, sequential effect, as I said. So basically, the idea is that what you have done in the previous steps actually have a huge impact on what we will do in the next stage. So before the proposed work, actually people use like Markov chain, this kind of methodology to solve the problem. Okay, but unfortunately for Markov chain, this kind of algorithm, the time complexity and the kind of is very high. So it does not work that well. So in this case, so essentially, Hongzhi and his colleagues also propose a work very similar to the model that proposed for the spatial recommendation. So essentially, we still need to capture a user's personal interests, but at the same time, we also need to capture, like, given the current observed sequence, what is the interest so far? Okay, so it's kind of sequential kind of inference, right? So previously, like, given this location, what's the interest for this particular location or the cross preference for this particular location? But now it's like giving the current observed sequence, what's the interest? And how to bridge the two, essentially try to use additive model that try to combine the 2 parts. Okay. Yeah, I'm going to skip all those details. Let me see. Okay, so then they consider how they can like model different different seasonal effect on the temporal stuff. Okay, so I will briefly mention the other work he didn't include here, because I feel that work is kind of a trend of solving this spatial temporal recommendation in general. So remember that in the very beginning, we say that according to the current location-based social network, we can, for each event, we can collect information like user, location, time, and some other description of this event, right? So what we can do actually is that we can learn a kind of embedding. Okay, so we treat that these 4 things like occurred together, and then we can learn embedding for user, time, location, and if the 4th part is text, then we can learn embedding for the text. Okay, so essentially when you do a recommendation, so what would be the query? So the query actually is going to be the user at which time and which location, right? And then you kind of map this triplet into you compute a new embedding for this triplet and compare this embedding to this kind of event or spatial items. Okay, and you want to recommend the closest one to that triplet. Okay, so essentially, if I summarize everything, it's like for the traditional recommendation, the query is just the user, right? And for the spatial recommendation, the query is going to user combined with location. And for the spatial temporal recommendation, it's going to be user, location, and time. Okay, so they have recent work is doing embedding that embed all the things like user, location, item, and other text, all kind of things together. And finally, giving a query, which is a triplet, then you can find the most similar item to do the recommendation. Okay, so that's the idea. I think that work is very nice. I don't know why they didn't include that one. Okay, so now I just jump to the last part. So essentially, I want to kind of mention some possible research frontiers. Okay, so actually, it's not. So this is just our personal opinions. And you probably, like, I actually talked with people coming from industry. Actually, you do have your own challenges and fancy problems. So probably those could also be written down into those frontiers, right? So the first thing that when I discuss with people, I feel that actually efficiency is a big issue. Okay, so most of the current industry, they do not really using the link-based information to enhance the recommendation, although they kind of buy the idea, okay, links are helpful. But somehow they feel that the link-based computation, the cost is too expensive. Okay, so they're somehow reluctant to do that. So then I discuss with them, so if you have done some like embedding, network embedding, where that kind of solve your problem, they're like, but still it's very difficult to determine a smaller candidate set because you're never going to really compute the similarity between a user and all the possible items. Okay, so then probably I think a best way that try to build some like spatial index. Okay, so once you have index, actually you do not really need to look into the first item set. Probably you just wanted to looking at the index, spatial index tree. You just want to find the nearby items and then do a recommendation. But I believe the efficiency issue, like including our sampling strategy, right? Our sampling strategy is also try to solve the efficiency problem. And for Hongzhi, they also have some like recent publication addressing the efficiency issue in the Spatial-Temporal recommendation. So this is their book. And another thing, actually, this is what we just discussed. So it's like cross-domain recommendation. Okay, so it's like although in today's talk, when we say recommend for some items to the users, we say that they're embedded in a heterogeneous network. But usually for all my examples, like, okay, we just consider movie items, right? And the movie items are linked to many other entities and the user are linked to many other entities. But let's see, a user can have a lot of behavior to many different types of items. Okay, for example, different types of products, right? Or like watch movie and like reading books. Actually, if you look at the domains of those items, they are just very different. Okay, so how can we leverage items from different domains and to do the recommendations? Also very interesting. So right now, I think our framework can somehow solve this problem. Okay, so for example, books and movies actually are highly correlated, right? So you can actually infer something from books, even you do not have any information for like interaction information for the user and the movie. So you still can infer something through the books they have read to do the movie recommendation. I believe like the current framework can already partially solve that problem. But still, like without really look deep into this problem, I think there are a lot of challenges. Okay, so since we do not have this kind of data, so currently we just can provide some possible direction to go, but still it's kind of under exploration. Yeah, so last thing is that still like cold start problem. Okay, so although we try to use the heterogeneous information network to leverage this kind of issue, right? Because once you're embedding a very complicated setting, actually you have more information, and this cold stat or data sparsity issue will be somehow be alleviated. But still, we have this kind of issue. So now especially when the user just join some system, you really know nothing about him or her. Okay, even you ask her, the user to provide some like personal information, but usually people just do not want do that. Okay. So right now I see some like system like force you to select some categories, right? But I think the first recommendation is very important. If the recommended category is not really relevant, right? So actually there's some kind of initial bias. So then how we can, based on very limited information, to do the very start recommendation, this is also a very, very challenging problem. Okay. So here, of course, there are other things like country for recommendation. We just consider like single direction recommendation. I just recommend a product to you. But in some system, like online dating system, it's very different. So it's like when I recommend someone to you, okay, I really expect I can get some reply. Okay. So for example, I recommend a gentleman to a lady. So I really expect the lady will have some response to the gentleman, right? So that's why you cannot consider, okay, that once you're done the recommendation, you're done. You need to consider whether you can really close this two-stage kind of connection. Then you're really done, okay? So, and also, it's also kind of a tricky problem. But anyway, so there are a lot of interesting problems to go, and depending on the applications, and you will see a lot of interesting new challenges. So here I want to like give a big summary to the whole tutorial. So essentially, the message we want to deliver is that if you look at recommendation, okay, it's not just a user item, okay? User item contain a lot of other information. Okay, and heterogeneous information network is a very good way to view the very complicated scenario they are in. Okay, because user item interaction embedded in this heterogeneous network. Okay, and for us, we find that treating the recommendation as sort of link prediction or information network mining problem is very helpful. And also, we have introduced like when we have a lot of text information, actually, it's probably a good way to first turn the text into some network. So we need to extract like phrases, the concepts, and treat them as nodes. Because for text, like what we're really interested in are the semantic meanings, right? So not a bag of words. It's kind of a simple representation. And also, when we look at a spatial-temporal recommendation, it brings even more challenges. Although I didn't do a great job for the last part for spatial-temporal recommendation, but I really suggest you to read the tutorial slides and maybe their papers to understand what they are doing. Okay, so if you still have questions, I'm still here, and I'm happy to answer those questions. Thank you.